we're hopefully here on the precipice of a really exciting chapter in humanity where we are going to start to go back to the types of innovation that we were doing in the 50s and 60s in terms of fundamental tough tech innovations.
Welcome to the Business for Good podcast, a show where we spotlight companies making money by making the world a better place. I'm your host, Paul Shapiro, and if you share a passion for using commerce to solve many of the world's most pressing problems, then this is the show for you. Hello and welcome to episode number 102 of the Business for Good podcast. I hope you enjoyed the last episode with drone seed. It was really cool to learn about how to automate the reforestation process. And we continue to get a lot of comments about episode number 100 with billionaire investor Steve Jurvetson. Definitely go back and listen to that if you haven't gotten a chance to check it out yet. So I hope that you are enjoying a nice holiday season. I hope that you're getting to spend time with your friends and family. And I guess most of all, I hope that you weren't invested through FTX. That's definitely a whole episode sometime, maybe, that we can talk about that. But for now, we're going to be talking about a really cool company called Quaise Energy. So you already know that the inside of the Earth is pretty hot. It's really as hot as the surface of the sun, which was amazing to me. I didn't believe it, but it turns out that's actually true. That heat could generate unbelievable amounts of clean geothermal energy to power our civilization if we could reach all the way down there to get it. To get fossil fuels like oil and gas, we only need to drill down a couple kilometers. In places that have volcanoes, like in Iceland, you can fairly easily reach into the hellish parts of the earth to harness geothermal energy, but most human populations tend not to be crowded around active volcanoes for obvious reasons. In the places where power plants typically exist, near human civilization, we would need to drill more like 10 to 20 kilometers down, which just isn't really possible with conventional drilling techniques in order to get to the geothermal energy that we want. Enter Quaise Energy, a 4-year-old startup that has now raised $70 million so far to drill deeper than humans have ever gone. Their plan is not to use mechanical drill bits, which are limited in their utility at such deep depths, but rather to vaporize rock using microwaves. Their plan is as bold as it is simple. Drill thousands of these 8-inch wide but super deep holes right next to existing power plants. That way, the plants can run on geothermal energy and stop using coal and create all the energy that we currently use daily. If it works, it is a rapidly scalable solution to quickly slash our fossil fuel use and avert the most catastrophic climate scenarios. Our guest in this episode is Quaise Energy CFO Kevin Bonebrake, cool name, a guy who spent most of his career in the conventional energy investment world and is now working to build a cleaner, safer, and saner way to power human civilization. I really like this episode. I got to learn about what the deepest hole ever dug was, so stay tuned for that. It's going to be a cool, fun fact for you in this one. So enjoy this interview with Quaise Energy CFO Kevin Bonebrake. Kevin, welcome to the Business for Good podcast.
Thank you for having me.
Hey, it's really great to be talking to you. I want to get down to business here. I guess actually, literally, I want to get down to business. So we're getting down into the middle of the earth here. Maybe not the middle, but pretty far down. Let me just talk just briefly before we get to what Quaise is doing about energy in general. If you think about the energy that we're using to power our civilization, we all know there's this big problem that the lion's share of it is coming from fossil fuels, and that generates greenhouse gas emissions, which are warming up the planet. So if you look at the ways that we can generate energy without fossil fuels and that don't have that type of carbon intensity, you think about solar and wind, but there's not that much geothermal that is happening right now. Why is that? Like, why isn't there more geothermal online? Like, why is everybody putting solar panels up, but you don't hear of that many geothermal projects?
Yeah, that's a great question. And the reason historically is that when you think about conventional geothermal, traditionally you had to go someplace like picture Yellowstone National Park. So you needed the overlap of heat near the surface, a reservoir that could hold water, and then a pathway to get to the surface for that water to be heated up to turn to steam, and then you would attach it to a power plant. So the number of locations on the planet that have those three items overlapping, which is the heat and the reservoir and the permeability, are pretty few, and they tend not to be right next to New York City or your major load centers. That has held it back historically, and also there's been a fair amount of exploration risk, and the drilling costs have been high. So I'll pause there.
Okay. So that would help to explain why places like Iceland, for example, right? Like they have a lot of geothermal because they have a lot of volcanoes. So presumably it's easier to get down to where it's hot underneath the ground.
That's exactly right.
Yeah. For way of background, like the further toward the core of the earth you get, the hotter it gets, right? It's like hell down there, right?
That's right. So the Earth actually generates 40 terawatts of energy per second. And humanity right now, if you look at all primary energy sources, consumes about 20 terawatts per second. And the source of that heat with the Earth is roughly split 50-50 between primordial cooling. So the Earth was originally formed and it was very hot when that happened. And so the center is very warm and that heat is radiating outwards. And then secondarily, there's radioactive decay that's generating the other half of that 40 terawatts.
I've heard, Kevin, that actually the center of the Earth is not that different in temperature from the sun. Is that true? Or this sounds like a legend, but is that actually true?
It's actually true. The center of the Earth is about 6,000 degrees Celsius, and so is the surface of the sun. Now, if you go to the center of the sun, where all the fusion is occurring, it's about 150 million degrees.
Yeah, I feel like
the surface of the sun.
So I've heard this is true. You, as an expert, are telling me that this is true. But if the center of the Earth is the temperature of the surface of the sun, yeah, that seems pretty hot. Why aren't we all burning up? Like, why isn't that heat frying us? And if the Earth were closer to the surface of the sun, we would have no life on Earth. So why are we not frying?
Because the Earth is a sphere, right? It's a ball, and when you think about that energy that's at the center, it's radiating out in all directions. And so when you divide that over the surface area of the Earth, by the time it radiates out, it's a much lower temperature. But if you go towards the center of the Earth, temperature does increase on average at about 20 degrees Celsius per kilometer that you go down.
Got it. Okay. So basically the premise is that the further down you go, the hotter it gets. We want heat in order to spin turbines so that we can have clean energy. Am I getting the basics right?
That's exactly right. And more specifically, we want steam that's at a temperature and pressure sufficient to plug into the existing coal-fired infrastructure so that we can kill two birds with one stone. So the first bird is we're going to make geothermal a lot more power dense and a lot more economically efficient than it has been historically. And the second is instead of building a geothermal plant to the specifications of the steam that's naturally coming out of the Earth, we're going to manufacture the steam to fit the existing power infrastructure. And what that's going to allow us to do is fix the climate change in a reasonable time frame, i.e. by 2050, which is on everybody's roadmap here.
Mm-hmm. Okay. First of all, as a bird lover, I don't want to kill one or two birds, so I hear you on that. In fact, I joke around. I like using the term to feed two birds with one, although it usually just gets me made fun of rather than anything.
I'm going to use that. So
Thank
I'm
you.
based here in Houston, and it is actually a great place for bird watching.
Great. Yes. Very good. Yeah. You want to solve the climate problem, but we want birds around in that climate too. Anyway, so you're going to feed two birds with one stone here with what you're doing, but we haven't even gotten into yet what you're doing. So you're basically talking, Kevin, about drilling a really deep hole. So I was looking into this and I was like, what's the deepest? And remember, like your kids and people are talking about, like, we're going to dig a hole to China. It takes a long way to get to China and you're going to burn up if you try to do that. But the deepest hole that was ever drilled by humans seems to be done by the Russians. And as far as I could ascertain, just to see if they could do it, I don't even really think they had a purpose for it. It wasn't like geothermal they were after, but it was 12 kilometers that they drilled down, and it took them like 20 years to drill this 12 kilometers. So 12 kilometers down, it took them like 20 years to get down there. You're talking about going even deeper. You're talking about drilling a 20-kilometer deep hole. For people who aren't familiar with the metric system, that's many miles drilling a hole down. If it took so it took the Russians decades to get down 12 kilometers, but you're saying that you can do this rapidly to get down to 20. Excuse me, it took the Russians decades to drill down 12 kilometers. You're saying you're going to get down there rapidly to get to 20 kilometers to get to the source of all this heat. How are you going to do it?
We are going to use a new drilling technology, and that technology consists of microwaves. So if you think about your microwave oven in your kitchen, the way that heats up food is that it uses a physics phenomena called dielectric heating. So what it does is it rotates the water molecules with electromagnetic waves, and that imparts kinetic energy to the water, which heats up the food. So we're doing the same thing, except we're using microwaves that are more powerful, and instead of food, we're heating rock. And if you heat it enough, it vaporizes.
What happens to those vapors? They just go up into the air? Like, are you digging this hole? Like, presumably what you're digging, you have to excavate from the hole, right?
Yep, and these would be 8-inch diameter holes to give you a sense of the size. And then when we're talking about going 10 to 20 kilometers down, the radius of the Earth is about 6,500 kilometers and 4,000 miles. People will frequently make the analogy that the skin of an apple is, if you compare that to the Earth, the skin of the apple is about the thickness of our atmosphere, which is 100 kilometers. If you think about the depth relative to the Earth, although it sounds like we're drilling really far, we're only drilling about 20 to 40% of the skin of an apple in comparison. That's how shallow we're going. But in terms of your direct question of what we do with the particulate matter that comes from the hole, we actually blow air down the hole in order to purge the particulate matter out of the hole, and it comes back up to the surface and we capture it.
So just so I make sure I heard you correctly, Kevin, you said the hole is 8 inches wide. Is that right?
That's right.
Wow. So this is almost imperceptible as far as land use is concerned.
That's right. That's right. From a power density perspective, it's on the same order of magnitude as fossil fuels in terms of how much energy you get out relative to the amount of surface area of the land. And that's about 10 to 100 times more efficient than other renewable technologies.
Yeah, you're using a term that many people may not be familiar with, Kevin, power density. So let's just talk about that for a second. There's lots of ways that you can generate power, right? You can burn fossil fuels. We can do nuclear fission. Maybe in the future, we'll be able to do nuclear fusion. There's solar panels, there's wind turbines, and so on. And all of these are ways of creating energy, but they're not equal in terms of power density. So why don't you just describe what power density means and why it's important?
Sure. So broadly, it can be defined in different ways, but people talk about how much land, material, and labor and time do you need to generate a given amount of power. So if you think about the amount of land that a solar array covers, and then you compare that to the amount of hole that one of our wells would cover, we would use about 1/100th of the surface area that solar would, for instance.
Just sorry to interrupt you here, Kevin, but just to be clear, what you're asserting is that to produce the same amount of clean power, your type of geothermal energy would use 1% of the land that would needed to be covered with solar panels to get that same amount of energy out.
That's correct. And actually that same phenomenon is why fossil fuels continue to be so popular, because there you're not looking at land density, but you're looking at density by volume and weight. When you think about what you do with energy, you need it for transportation. You need it to travel along with you frequently. And that is why fossil fuels have continued to be so popular relative to other forms of electricity. You think about the weight of batteries just to store electricity in order to power electric vehicles. And that right there, you can see, I mean, like a Tesla weighs about 5,000 pounds, and most of that is batteries, for instance. So this is an area that people are increasingly becoming aware of, because the question is, how do you scale renewable technologies in order to power the whole world?
Yeah, so that's really interesting. And you mentioned oil and gas and these other fossil fuels that we're using that are emitting all this carbon into the atmosphere. To get down to there, to where these reserves are, it's generally 2 or 3 kilometers down, right? So you're talking about going many times more down. Like if they're only going 2 or 3 kilometers down, you want to go 20 kilometers down. Obviously, there's a geothermal play there. Is there also an oil and gas play for that technology? Like they use mechanical drill bits, right, to drill that far that down. The problem with using mechanical drill bits when you start getting that so deep is like the rock is really hard and it's also really hot down there, and it doesn't really work. So presumably your microwave technology can do it, but are there also reserves of fossil fuels down there? Are you inadvertently opening up more exploration for fossil fuel deliveries as well?
We are not. And the reason is that our technology works best with silicates, which are the type of rocks that you find in the crust of the earth, which are broadly granites and basalts and quartz and feldspar and rocks like that. So hydrocarbons are found in the sedimentary layers, which tend to be shallower. And in fact, when we're drilling through the sedimentary layers, we'll plan to use conventional drilling technology just to make sure that we properly drill and complete and case the well so that we don't have any interaction with hydrocarbons or water aquifers or anything else. So no, we will not be using this for hydrocarbon exploration. That drilling for hydrocarbons, the first well in the modern era was the Drake well in Pennsylvania, which was drilled in 1869, I believe. And so that drilling technology has been under development for 160 years. So we're not looking to improve on that.
Got it. Okay. If this is 8 inches wide but you got to go really far down. How long is it going to take? Like, how long does it take you to get down 20 kilometers? I know that you haven't done it yet, but how long do you project it'll take?
Yeah, we think it'll take for a 20 kilometer, it would probably take about 200 days.
And why do you emphasize for a 20 kilometer? Are you implying that you might do shallower wells as well?
Yes. So the geothermal gradient, which is how fast the temperature increases as you go down into the earth, it varies all over the planet. So if you're in Iceland, you could hit the temperatures that we want to hit, which is about 500 degrees Celsius. You could hit those kind of temperatures at 5 kilometers down. But if you're in a low geothermal gradient area, you'd have to go 20 kilometers down. But 10 kilometers down, we think will be sufficient to repower half of the planet with these types of power plants, and 20 kilometers should be sufficient for about 95% of the planet.
Got it. So are you planning to first go down 10 and then at a later time do 20? Is that the idea?
Yeah, so we'll, just like any kind of new technology, we have to walk before we can run. So our next couple of steps are to demonstrate that we can drill to 10 meters, 100 meters, 1,000 meters down. And then we're going to demonstrate that we can drill into temperatures that are much higher than any existing drilling technologies can handle. And then we'll repower a power plant that's on top of a high geothermal gradient where it's relatively shallow, and then we'll get progressively deeper over time.
That begs the question then, Kevin, what's the biggest hole that you have drilled to date? Like, how proven is this type of microwave technology for drilling holes?
To date, we have not drilled very deep. We've drilled just a couple of inches.
Okay.
Actually. Yeah. And the reason for that, though, is we're not held back by physics. All the physics here says we should be able to do this. It's just that we have been using equipment that was essentially donated to us after we founded the company a couple of years ago. We took that equipment and we built a prototype at Oak Ridge National Laboratories in Tennessee. And we demonstrated to investors that this would work on a much larger scale than had been done at MIT, which is where this technology comes from. It comes out of the MIT Plasma Science Fusion Center. We demonstrated we could do it at a much larger scale. And then we just closed our Series A and raised $52 million of proceeds earlier this year. And the major use of that proceeds was to order equipment that is specifically built for this application, at which point you're going to see a rapid advancement in the depth of our holes.
Congratulations on a very sizable Series A. 50 million is obviously nothing to sneeze at. Obviously, your 2-inch hole was impressive for these investors to pump tens of millions of dollars in. So congratulations on that. To date, my understanding is the company's raised about 70 million to date. Is that right?
That's right. 75 million. Yep.
Every million counts. So 75 million. Okay. So in the last 4 years, you guys have raised 75 million. You now want to actually build the equipment where you can start drilling down a lot deeper than the 2 inches that you've already done. When will that be? Like, when are we going to start seeing Quaise holes in the ground somewhere?
So in terms of the history of the company, from 2007 to 2017, MIT was conducting experiments at their laboratories at the Plasma Science Fusion Center. Our founder, Carlos Araque, was a senior Schlumberger engineer. Schlumberger is the largest oil field services firm in the world. So he took that technology, he founded the company, took that technology out of MIT and to the national lab. So Oak Ridge National Laboratory is funded by the Department of Energy, and we had a Department of Energy grant. It was there that we put our first prototype together. So out of academia and into the national labs. And now what we're doing is we have an engineering center in Houston, which is where I'm based, where we are demonstrating the holes to a deeper depth. And sorry to give you a long-winded response, but that's basically what's been going on for the last year or so. The next 2 years, we are going to be going out in the field. So we will be taking this technology that, although it's been around since the 1970s, it's only been used in fusion experiments, which are very clean lab environments, and we're going to take it out into the field and drill wells in the great outdoors. And then that'll be by 2024. By 2026, we'll drill a hole in the 500 degrees Celsius temperatures and produce steam that is of a temperature and pressure quality that you could fuel a power plant. And in 2028, we will retrofit a power plant and show that we can hook up one of these geothermal fields to existing infrastructure. So that's the timeline.
Got it. So your investors must be pretty patient then. Like, you're not going to really have anything commercial for several years, and you've already been around for 4 years. So they must think, hey, energy is a gigantic market. We're going to need more and more clean energy, and this is going to be the future. You are the CFO. Right. You're the CFO. Your background prior to working at Quaise was in energy investing yourself, working at like Morgan Stanley and doing other energy investments. So what led you to switch sides of the table here? What led you to want to stop investing in energy projects and start being one of those energy projects yourself?
It goes pretty far back. I've always liked building things. And in college, I double majored in mechanical engineering and economics. And then I briefly did some engineering, coincidentally, in laser applications, which is related to what we're doing right now. But then I went down this path of investment banking for close to 20 years. And I ended up specializing in energy. I moved from New York to Houston. I'm sitting in Houston, and Houston has one of the greatest concentrations of mechanical engineers and finance people and legal people, largely as a result of the oil and gas sector. So when you think about certain segments of energy transition, and I'll just name a few. So specifically geothermal, which is what we're talking about now, but also carbon capture and sequestration and hydrogen. Houston is really developing into a nexus for that type of work. And I was very cognizant of that as an investment banker, because in covering my traditional energy clients, they were always asking me for my views on up and coming technology. And I met Carlos, who's our founder at Quaise Week, which is a big annual energy convention. And we started talking about the company, and he invited me to join. And I couldn't say no, because I saw just how transformational this is going to be. I could appreciate it from both a technical and a finance perspective.
That's cool. Well, out of curiosity, what does Quaise mean? I don't even know what that word means.
Yeah, it means the end of the peninsula. It's actually a location on Nantucket off of Massachusetts. Our company was founded with MIT technology. Some of the people up there have a penchant for naming companies after geographical landmarks in Massachusetts.
That's cool. All right. Speaking of MIT, then, they own part of I presume this is a patented technology. So is MIT going to financially benefit from the success of Quaise?
Yeah, they will, is the short answer. MIT owns a venture capital fund called The Engine, and The Engine is focused on tough technology, which is a term that they coined, but it's basically biotech, manufacturing, aerospace, all these technologies that are hard technologies, and they are our lead investor.
That's great. That's great. Let me just ask, without presuming, there is patented technology here, right?
Oh, yes. Excuse me. Yes, we have a number of patents on this technology, and some of those are patents that we have licensed from MIT from that period when they were experimenting with this technology in the fusion labs, and then other patents are ones that Quaise has filed since the company was founded.
Got it. These are granted patents or pending patent applications?
Granted, and there's a few that are pending, but the core technology has been granted.
Got it. So if somebody else wants to come and start a company, they're going to say, hey, cool idea, we're going to do it. What's the moat like for Quaise in order to protect itself from copycat companies that want to figure out some better way to drill this big hole?
Yeah, the moat is pretty substantial, actually, in that although the physics are proven, the engineering applications are not. So actually taking these existing technologies and applying them to drill a hole is something that has never been done from an engineering perspective. And the reason that we are well situated to do it is that the majority of our engineers are former oil and gas R&D and product development experts. And we have, when you look at our company, about 90% of our company are people with physics, mechanical engineering, electrical engineering, RF engineering degrees, and a fair number of them have PhDs. And then we have a whole group of contractors that are helping us out as well that are at the PhD level. So it's actually pretty difficult to replicate what we're doing in terms of from a know-how perspective.
Okay. In terms of the know-how perspective, Kevin, I do want to ask you about how you will what you'll do with this energy when you bring it up to the surface, right? So you're going to transport all of this heat, hundreds of degrees Celsius down there. You're going to transport all this heat. And then what's going to happen to it? Like you alluded earlier in the interview to being next to a coal power plant. Is that what you want to do? Just build these next to coal power plants and have them run on geothermal heat rather than coal produced heat?
Yeah, big picture. Yes, that's correct. So that actually, though, once you have the steam at the surface, it's all very established applications. So just transporting the steam to the power plant and connecting into the power plant, the geothermal industry has been doing that for a long time. So essentially what we're doing is we are replacing the boiler in the coal-fired power plant. So right now, coal plants pulverize coal, they light it on fire, that heats water to steam. That steam has a bunch of energy. As it expands through a turbine, you convert that energy to a rotating turbine that is connected to a generator, and you get your electricity. So what we're doing is we're just replacing the boiler.
That's really interesting. So you don't need to create an entirely new infrastructure in order to do this. You just basically could take an existing power plant and run it on geothermal, because you could drill the hole right outside of it. You don't have to transport it long distances. Am I correct in thinking that?
That's exactly right. So back to let me see if I get this right, feeding two birds with one scone.
Very nice. Very nice.
Yeah, this is not just transformational in terms of taking geothermal technology and drilling and completing wells that are 5 to 10 times as productive. It is doing that, but it's also using the existing infrastructure. And that's super exciting from an economics perspective. But what's even more exciting about it is if we're trying to clean all the carbon out of the air by 2050, and we're looking at a bunch of new technologies to do it, say you get a new technology to work, how long does it take you to actually build enough power plants and enough transmission infrastructure interconnects to replace 10,000 coal-powered power plants, which is the number of coal-powered power plants that are around the Earth right now. So how long does that take? It certainly takes longer than 20 years. So with our technology, we're just plugging into the existing infrastructure, which is going to enable us to deploy this extremely rapidly compared to other ideas.
If it works, that would be pretty exciting. The idea that you could drill an 8-inch hole adjacent to a current coal power plant and just run the same exact power plant, but instead of buying coal, they just buy the Quaise Energy from you. That seems like it would be a pretty awesome thing. It's pretty exciting. So let me ask you then, Kevin, obviously, I hope this works. It would be magnificent for the world if you guys could do this. I'd love to see one of these holes. It'd be pretty interesting, like if there's any microbial life down that deep that could survive those types of extreme conditions too. So that might be another interesting part of this, to find some cool new microbes that can do something awesome for our world as well. But let me ask you then, like, you've had a career in energy investment and now in energy entrepreneurship. Have there been any resources for you, Kevin, that you think would be useful for other folks, whether they be books or anything else that you would recommend to other people to check out that you would say, hey, I liked this, you might like it too?
Yeah, certainly. So look, from an energy specific perspective, the most useful books to me, I'd say energy specifically, I would point people to an author named Vaclav Smil. So he wrote a book called Energy and Civilization that talks about how to think about energy densities and the impact they've had on humanity. He also wrote a book called Power Density that talks a lot about these concepts that I was referencing in terms of land, material, and labor intensities relative to how much energy you get. And then from a general perspective, there's a book called Loon Shots that came out a couple of years ago that has been super influential to our thinking, which is how do you structure an organization in order to repeatedly nurture innovations and breakthroughs that we found very instructive as we think about how to take a technology heavy staff and marry that up with the big commercialization and strategic questions about how we deploy this technology around the planet.
Cool. Yeah, I'm a fan of Vaclav Smil's too. Like most people, I learned of his work through Bill Gates promoting it. And then I started reading his books and I was like, wow, this guy has a lot to offer. And I've learned a lot from reading his stuff. And I was talking with a colleague of mine who recently read a book of his called Growth. I don't know if you've heard of that one, but it's a book called Growth from Microbes to Megacities. It's all about how structures grow in the world. And I haven't read it, but I heard it was phenomenal. Cool. And so I intend to read it, although I did look at it and it was like several hundred pages long. So the growth of his book was a little too ambitious maybe, but I look forward to reading that as well. Cool. That's awesome. And we'll link to those books on the episode page for this podcast at businessforgoodpodcast.com. So finally, Kevin, obviously you have chosen to join Quaise and you're going to dig some epically deep holes and get some really inexpensive energy that is carbon free to the surface. But are there other ideas that you wish that somebody else would do? Something that if you weren't doing this, maybe you would do, or that you think the world needs?
Yeah, look, I think in terms of solving the climate crisis, and specifically from an energy perspective, it is, to use a cliched term, an all of the above kind of situation where everybody needs to try everything to be successful. Beyond geothermal, I think ideas in smart grid technologies, hydrogen for transportation, carbon capture and sequestration, or to keep using fossil fuels but bury the waste. I think these are all super exciting ideas, as well as modular nuclear reactors. But overall, I think we're hopefully here on the precipice of a really exciting chapter in humanity where we are going to start to go back to the types of innovation that we were doing in the 50s and 60s in terms of fundamental tough tech innovations to, again, quote the term that MIT coined in mechanical and chemical engineering, bioengineering, all that kind of stuff. So that's a pretty broad answer for you, but I'm excited about the future.
Yeah, so that's pretty exciting to think about. You mentioned modular nuclear, and obviously there's efforts to do modular nuclear fission, but there's also a crop of companies now that are promising that they're going to bring nuclear fusion to the world as well. That's the type of nuclear reaction that occurs in the sun, where you're not splitting atoms, but you are fusing them together. And let me just ask you one provocative question then before we go, since these are both, since it sounds like these are both futuristic technologies that haven't yet been proven out in the real world, but they physically do seem to be possible within the laws of physics. So what are we going to see first? The first ever Quaise Energy generated geothermal energy produced plant, or fusion nuclear?
I think the former. So a Quaise Energy geothermal plant, but I will say that nuclear is a close cousin of ours and we know a lot about it. Sorry, when I say nuclear, I'm nuclear fusion. So fusion is a close cousin of ours and we know a lot about it. And we do think that fusion is going to be what powers civilization for 100, 200, 1,000 years from now. But is going to be the other part of that. And geothermal should be easier from an engineering practicality perspective, but we're also optimistic that fusion is going to work. It's just going to take a little bit longer.
All right. This is a bet that will go down, and maybe 5 years from now we'll revisit this and we'll see how we are obtaining energy at that point. So I hope they're both online by then. That would be wonderful. But Kevin, I really appreciate what you and Quaise Energy are doing to try to solve the climate crisis. Congratulations on your fundraising success, and I hope it becomes a commercial success too.
All right. Thank you. Really enjoyed the conversation.
Thanks for listening. We hope you found use in this episode. If so, don't keep it to yourself. Please leave us a 5-star rating on iTunes or wherever you get your podcast. And as always, we hope you will be in the business of doing good.